Good morning and welcome to everybody to today's seminar on bias in AI, the politics of data and algorithms. And today we will have two presentations that will continue actually to explore how biases in artificial intelligence arise and what role data, algorithms, and their underlying principles play in shaping these systems. Tobias Matzner, welcome. We'll start by questioning the common focus on bias training data as the sole issue of AI or in AI. And he'll show how data and algorithms actually work together and why we need to consider both of them, and then also revisit the history of AI to understand more about these biases and the structure of these biases. And then next, Mary Schneien will dive into the mathematical foundations of AI systems, and she'll look at how these principles create categories of difference and reflect societal ideas about race and gender and these kind of categories, class, and so on. And then after the talks, my colleague Iris Lorscheid will offer a commentary to connect the key points, followed by a short internal discussion, and then we will open the panel for a broader discussion. And I'm actually quite excited for the various perspectives that we are having today. So on one hand, Mary and Tobias coming from the University of Paderborn, and then on the other hand, Iris Lorscheid coming from UE, having a background in hard sciences, actually. And I think this is the first time that we have this kind of perspective here in our seminar series as well, which I think is important that we, also get the discussion more and more started in this interdisciplinary way. So I will introduce Tobias Matzner now, who actually studied computer science and philosophy in Karlsruhe, Rome, and Berlin, and completed his doctorate in political philosophy at the Karlsruhe Institute of Technology. He then worked at the International Center for Ethics in the Science and Humanities in the University of Tübingen, where his research focused on security technologies, and then the New School for Social Research in New York, where he explored privacy in the context of digital media. Since 2017, he has been a professor at the Institute for Media Studies at the University of Paderborn, and there his research is at the intersection of media and technology theory on one hand, and political philosophy and critical theories on the other hand. And Tobias, I would say the floor is yours, and we are very much looking forward to your presentation.
Thank you so much. And thanks so much also for giving me the opportunity to speak in that super exciting lecture series and to such a broad audience. Usually those discussions are in quite confined circles, so I really love that format. As Jiré quickly mentioned already, I want to focus on a common topic in discussions about biases and AI and amend that a bit. So I guess you all know the story by now that machine learning or artificial intelligence, I'll use machine learning from now on because I think it's slightly better term. It has its own problems, but at least it doesn't come with all the sci-fi associations that we have with artificial intelligence. So in machine learning, a lot hinges on the data. And if you have bias training data, these biases kind of propagate through the models and then the applications. And these are super important points. I don't want to say that's wrong. I just want to say it can lead to a bit of a too narrow perspective. And that too narrow perspective is easily captured with a phrase that is common in computer science, which is called bullshit in, bullshit out. That is, when you feed bad data in, you get a bad result. And that kind of makes everything else a neutral channel, right? If you put something bad in, something bad comes out. If you put something better in, something better comes out. And that is, of course, not the case. So the algorithms, the target or cost functions, the context of application, they all play a role. And I want to focus particularly on one element in that huge complex interplay, which are algorithms, and show how algorithms are important in creating the meaning that data apparently have but I don't want to go as far as like advocating for a kind of algorithmic idealism, one could say, where the algorithms read the meaning into the data, but rather show that algorithms are a medium in the sense that they relate several contexts of application where these data have different meanings. And at least there's the context of training, the context of application of a machine learning system. There might be even more, but these two are there in any case. And I want to argue that that relationship that algorithms create really are what makes the meaning of the data. So data are important, but only in that related fashion. And that is also kind of the basic position or the basic point of view where we can think about biases in a more complex fashion. So my talk is a bit like on the really fundamentals of how to conceive of the meaning of data in the first place to then get a better understanding of bias. And to show how that meaning or that relationship that creates the meaning or changes the meaning of the data comes about, I want to dive a bit into the history of machine learning, just because I think at that point in the history of machine learning in the 1980s that I will be talking about, that very feature of a particular way of understanding or conceiving of data was still a matter of debate and thus very clearly discernible. Today, it is just a matter of course in machine learning. And so I think going back to that route was really helpful. And that historical work is joint work with Amira Möding, who's in the history department in Cambridge and also affiliated with the Center of Digital Humanities there. So lots of credits go to Amira for that section. And if you're more interested in that, really go and talk to her. She's much more knowledgeable about that history than I am. So what I want to talk about quickly is a group at IBM in the 1980s, 70s, 80s that were tasked with creating a speech recognition system. And back then, the general idea was when you want to create a speech recognition system, you need some knowledge about speech, grammar, vocabulary, and so on and so forth. So basically what linguists do. And you need to take that linguistic knowledge and encode it somehow into a computer system, right? And then you can create a speech recognizer. And that was the predominant theory, and it didn't work too well. And then at IBM, a group started to take a completely different approach. They did not turn to linguistics. They turned to a man called Claude Shannon, who was an information scientist at IBM and had created a very simple model for electronic communication, which he called the noisy channel model, which is basically just an input, then you have a channel that kind of distorts the input a bit. So at the output, you get a distorted version of the input. And then Shannon conceived of a purely statistical way how to reconstruct the distorted signal at the output. So basically, statistically guessing what is the most likely input given the output you observed. And he did that, and that is the important point, completely ignorant of the content of communication. It was just about the likelihood of a symbol to appear. But if that communication was about letters or numbers or sentences or English or Japanese, didn't matter. As long as you could say anything about the distribution of probabilities of the individual messages, you could use that method. And that sort of content ignorant theory of information, that's what the IBM group took up and said, that's how we do speech recognition. Basically, what we have is a bad channel, right? So I have a word in mind, and I want to convey that word to you, but I use a channel called spoken words, and you want to reconstruct the word I had in mind. So it's basically the same situation, right? I have a bad channel, spoken audio, spoken voice, right? Which is a bad channel for words. And so they applied that idea, a purely statistical estimate, to speech recognition. And Fred Jelinek, who was the head of that group, became quite famous in computer science with all kinds of braggadocious quips, like every time I fired a linguist, my speech recognizer became better. just to make that point, he didn't need any linguistic language anymore. What he needed is data, lots of data. And of course, here we have the sort of socio-technical or economic background. That was IBM. It was not a university. It was not a small research institution. It was IBM, the biggest company for business machine that had loads of data available, right? And they had also loads of money to create even more data on purpose. So basically, that speech recognizer did nothing else than look for a statistical model. And then they used that statistical model to just match input data to output data based on the distribution of probabilities in each of them, without any knowledge that that is speech, right? And that is the important point. They turned a machine learning problem from something that needs to know something about the world to a pattern matching problem between input data and output data based on statistics. The technology they used back then are so-called hidden Markov models, which were a technology that was created in American military research. And to this very day, I haven't found out why or for which purpose. It was published in purely mathematical terms without any application. It was just sort of, here's an algorithm how to estimate the parameters of a statistical model, right? But I know that it was created at an American military research agency. I don't know for what purpose. But IBM used that model back then, but it was the very same idea that animated the so-called backpropagation model that was published in the early 1980s, and which is to this very day the algorithm that is used to train artificial neural networks. So whenever you see something that is made by an artificial neural network, speech recognition, but also all the fancy large language models or foundation models, as they're now called, that large ChatGPT, anything, all of that is trained with backpropagation, which is again the same idea. You have data, lots of data, really lots of data, and you adjust the parameters of the model until the input data matches the output data based on some function that compares the two, right? So what emerged there at IBM and also at a few other places, but at IBM, they were most vocal about that change, is a new idea of data, right? So they said, I'm not interested in data anymore as traditional empiricism would have it. Data should be a good representation of the world, and good data is a good description of the world. And that is explicitly what that group said, no, we don't need that, right? Data is only a matter of the relationship between input and output, which means, and that extends to artificial neural networks, you can't sort of take the model anymore and compare it to the world to see if it learns something. The only way to see if an artificial neural network learns something is to run it and see its performance, right? Monitor its performance on data. So neither has the data meaning in and of itself, because if the data is a good description of the world, that does not mean necessarily it's the best data to do that statistical estimation. On the other hand, the algorithm in itself, or the artificial neural network in itself, does not have meaning either, because that is essentially the black box problem everybody talks about. You need to always compare input data to output data, or rather, you need to run it and see how well it performs. And how well it performs can only be gauged against some test data. So you need, again, data to do that. And this is a huge, actually, change in computer science, which, as I said, by now is a matter of course. But when you read computer science papers from the 1980s and earlier, they looked like math papers. They ended with a proof, quod erat demonstrandum, right? That's how you end a computer science paper. Today, the end of a computer science paper is a benchmark. Like, my model performed that well on that and that and that database. And that's a change, which I tend to call a performance-based understanding of data, right? So the meaning of the data is really just based on that performance. And to show you how that relationship between sort of input and output really creates the meaning, I quickly want to jump into a few examples. And the examples I want to use are embedding models, word embedding models. They are an essential ingredient in the most recently hyped artificial intelligence technologies like ChatGPT and so on and so forth. They were kind of at the start of all of this. And I use that model also because it is what is computable, tractable for pure humanities department in which I live, rather than a big computer science department. These word embedding models became quite famous by their feature to permit calculations on meaning. So this is the most famous example. So you should see my screen now. You have a model that models words, right? It models words by projecting them into a vector space. So that's the embedding. It turns words into mathematical vectors. And when you do calculations on these vectors, you actually get something sensible. That was the argument. So for example, if you subtract the vector man from the word king and you add the vector woman, you arrive at queen. And that was kind of the idea that that model actually learned something about the world. It learned gender, at least in a linguistic sense. You can do that also with other relationships. So for example, if you extract the word dog from the puppy and you add cat, so you ask, what is like puppy, what is like the puppy to dog, what's that for a cat? And you get kitten, which is right. You also got the usual gender stereotypes. So if you ask for something like a doctor, but as a woman, you get a nurse and not a doctor. And that was the huge outcry. And of course, that was right that that was the outcry. But that's not my point for today. That has been discussed a lot. I want to make a more fundamental point, which is about the way meaning is created in the first place here. So the explanation for this was, as I said, this is a vector space. And apparently just by being trained on a lot of data, that model has learned something. And it has learned something like gender, which is in that vector space represented as a direction, right? You can see that. So man and woman and king and queen, they are all in the same, related in the same direction. So that direction apparently means gender. But you can see that only, again, by asking the model stuff. So by calculation, the distance between man and woman and king and queen. And you can explore that dimension more by taking a list of words and ordering them along that apparent gender direction, right? And when you do that with those words, it seems to make sense. So when I order them from she to he, woman, girl, queen, nurse, doctor, cleaner, boy, mechanic, man, king, kind of makes sense. I mean, you can sort of argue and you can see a lot of stereotypes in there again, right? But you could say it learned something, even if biased, it learned something. To get away from these stupid gender examples, I just took a different list. I took a list of words and sorted them from sweet to savory. And again, one could argue, yeah, well, kind of works, right? But if you took a more complex list, you already see it's machine learning. It depends on the words being in the data a lot. So you see problems appear, right? So it doesn't make much sense, for example, that dessert is way more to the savory end of that list than cheeses, in my sense at least, right? And home fries are actually pretty sweet. So you get problems here, just based on sort of the quantity of the available data. But the problem extends. So I had my list of gendered words here, but I just asked the algorithm to sort them in the sweet savory dimension. And the algorithm does that. And it gives you an answer, which is as clear as the he, she thing. And before you start to try to sort of read any kind of meaning in how maybe boys and kings and girls are sweeter than doctors, I also sorted them from multiplication to reign, which you can do. And the algorithm gives you an answer because it's all vectors, right? And you can ask these questions. And that was actually inspired by a talk two colleagues from Cologne gave at the last CHAOSS Communication Congress, who used an image embedding. It's the same thing. It's used for these kinds of applications. You can ask how, like, which is the happier picture here, and apparently the right picture is happier. But you can also do this, right? You can ask which is the happier picture here. And I want to highlight that when you look at that number here below the sausage with sauce kind of thing, it's 20, and that face that really makes sense to be called happy is also 20 something. So the numbers aren't that much different either, right? Sorry. So that's, I don't know. So that's the point I wanted to.
It's weird because it's coming somehow from you, Tobias. I don't know.
Coming from me?
I don't know. It's like, I think there's nobody here in the.
But there's nobody here either. That's
Yeah, that's really, it's a ghost.
So anyway, I guess it's gone now. The point I wanted to make here is the difference between those quite sensible things that show that the model actually learned something and these silly jokes I just showed you is really on the relationship between training data and the queries I put into the model. If you train a model on faces and you ask them things about faces, of course that makes sense, right? But if you then feed schnitzels and sausages in that, there's nothing in the model that tells you that's nonsense. It is just the relationship of the context that we as human beings know that tells us, well, that's nonsense. And if you order a list of like occupations and people from sweet to savory, multiplication, terrain, somehow our social knowledge maybe can read some meaning into that, right? But again, it's not there, and there's nothing in the model that tells us this. And as I showed you, even the distances are not. There's no mathematical proof that says, well, it is kind of like this. It's closer. I mean, the measure in that vector space is always proximity, but it is not much farther away either, right? That's the sort of an illustration of the point I wanted to make. We have a relationship that the algorithm creates between the encoding, the training, which is a highly situated process depending on training data, the selection of training data, including all the biases that are present, and the decoding or querying process. And I chose this example now because in the very confined space of IBM back then, where it was all about language recognition or voice recognition, these two situations were almost the same, right? You have a person that dictates to their PC and wants to sort of say something and sees the words immediately on the screen. So here, that distance, that relationship that the algorithm creates is so small that actually you can forget it, right? But now with those apparent foundation models, that distance becomes huge. And it connects all kinds of, the model has been done, that model I used has been trained by Google somewhere in 2017, based on Google News data. And now I do all kind of stupid and sensible stuff with it. And there's now this talk about so-called foundation models, which are not foundation models, which were trained at a certain point for a certain purpose, but are sold to be reappropriated or fine-tuned to all kinds of different applications, which really means they establish a new relationship between that application and the training context. And it is that relationship that really creates the meaning of the data, and that creates the difference between sense and senseless data. And so when we want to talk about biases, and that's sort of the end now of that very technical talk, I have to admit, we can find some of them in the training data that will just pop out on the other end. But there is the risk of having even more biases that come about in that relational manner, not only by changing the meaning of the bias, which is part of the problem. So for example, in another text, I've argued that the meaning of suspicion completely changed. Suspicion has always been a very biased thing. You know, some people have always been more suspicious than others. But the way you become a suspect these days is, for example, by your browsing behavior online or by the motion tracking of your smartphone or things like that. So this is an electronic digital version of suspicion that creates new relationships, for example, between what you do on Instagram and suspicion, state surveillance, right? That hasn't been there before. These processes also transport biases to these relationships transport biases, pre-existing biases to new contexts, sectors of people's lives, and so on and so forth. But I want to stop here. I think this is important for discussion, and I already ran out of time. As I said, I just wanted to sort of make a very fundamental point of really how algorithms should be seen as creating a relationship between data in different situated contexts. And that is sort of the baseline, that performative meaning of data, right? That's based on the performance of an algorithm that doesn't read meaning into data, but creates meaning by putting different contexts of using data in relation. That should be the starting point for looking at biases, or that should be added when we look at biases to the focus on training data exclusively. Thank you so much.